awgYYVNDdPg. Bismillahirrahmanirrahim. Dear students, today we are going to do raw materials, flowsheet diagrams, and unit operations and unit processes of formic acid industry and its applications. So dear students, we have done production of formic acid in the previous lectures and some of the uses in the last lecture, lecture number 9. Now we are going to do today some other uses of the formic acid here in this lecture. So leather industry, the use of formic acid in leather industry. One of the biggest users of formic acid globally is the tanning industry. As the tanning industry has moved to lower cost countries, the growth figures in Asia have been very high, compensating the decline in Europe and North America. Now, China is the largest producer of the leather, and that is accounting for about 30% of the world production. So the tanning industry has been shifted to the lower cost countries, and its growth is increasing in Asia, and China is the largest producer of leather, and it is about 30% of the world production is being done by China. Now, for the pre-treatment of hides and skins, the conditions which are used, after the use of those conditions, the hides and skins are slightly alkaline after the pre-treatment. But for the tanning we require acidic conditions. So if the hides are slightly alkaline and we need acidic conditions, so the hides have to be treated with acid prior for tanning. Like acid will be used, like sulfuric acid or formic acid can be used, and this process of treatment of hides with acid is called pickling. So we can say that in the pre-treatment of hides and skins, they are slightly alkaline. We have to acidify them before tanning, and the process in which they are acidified using sulfuric acid and formic acid, this process is called tickling. Without this conditioning, there will be a drawback. Like if we shall use tanning agent, that will just be quickly settled down on the surface of the hide. That will be just fixed on the surface of the hide. It will not go into the inner layers of the skin or hide we are using, so that the inner layers will remain raw. They will not be, the dye will not, the tanning agent will not go inside the inner layers. So that will be a negative aspect of the process. Sulfuric acid reduces the pH of the liquor, while formic acid is capable of penetrating through the collagen fibers rapidly and homogeneously. The collagen fibers, the tissues which are present in the skin, they are made up of collagen fibers. So the pH is reduced by the use of sulfuric acid, and formic acid penetrates through the collagen fibers. So that penetrates and homogeneously penetrates. It ensures that the tanning agent, usually basic chromium sulfate, will penetrate the entire thickness of the hide. This homogeneous and rapid penetration of the formic acid into the collagen fibers ensures that our tanning agents like basic chromium sulfate, or if any other tanning agent is used, that will penetrate the entire thickness of the hide. In leather dyeing, formic acid is used as a leveling agent to aid in moving the dye from one area of the leather to another, so that results in more uniform and smoother dye distribution. Now the use of formic acid in textile. In the textile industry, formic acid is used as a pH regulating agent in dyeing wool, nylon, and other natural and synthetic fibers with acid and chrome dyes. So whenever the nylon, wool, and other natural synthetic fibers are dyed with the help of chrome dyes or with the help of acids, formic acid regulates the pH in all this process. In addition, formic acid is used to neutralize alkaline solutions and facilitate rinsing during laundering. Like whenever there is laundering takes place, laundering means cleansing of the fabrics where there are alkaline solutions which restrict or avoid the cleansing. They are just neutralized using formic acid. They will be neutralized and rinsing will be properly done during laundering. Furthermore, improving living standards and increased fiber production, especially for export markets, they are expected to increase demand for formic acid in textile dyeing and finishing in Asia. So what is happening, like in as the standards are being increased, fiber production is being increased. So now formic acid demand is being increased in dyeing and finishing of the fabrics for textile industry. Specifically in Asia, this is in great demand. Now for feed additives, organic acid and salts have a long history in the feed industry, which commonly uses them as a preservatives and for acidification of piglet diets. So organic acids and salts are also used for preserving food for the acidification of piglet diets. Organic acids are also used for this purpose. Since 2006, when the EU, European Union, banned antibiotic growth promoters, AGPs, the use of organic acids in feed has increased. So European Union in 2016, they banned the antibiotic growth promoters. AGPs, the use of AGPs was banned. So organic acids were started to be used more rapidly over there as a replacement of AGPs. Formic acid has a strong acidification effect, but also antimicrobial effects. It is used for the purpose of acidification. As along with that, it is having antimicrobial effects which are used to protect feed and drinking water against bacterial contamination. So if formic acid is used, there will be an incentive for the avoid or for the bacterial contamination will be just avoided or will be just prohibited using formic acid. Formic acid is very effective against Salmonella, Escherichia and Campylobacter at pH 4. So all these species, for all these species, formic acid is very effective against all these three at pH 4 especially. The formic acid acts positively on the gut flora of animals. The gut flora, where their digestion takes place, where the intestine and the gut is including these parts. And can improve both the apparent digestibility of energy and protein and the absorption and retention of some minerals. So what is happening that with the use of formic acid, there is improvement of digestion also, and there is improvement in the digestion of proteins also, and some minerals are absorbed well, and their retention is also, absorption and retention is also improved using formic acid. It seems to enhance the gross performance of weaned piglets and fattening pigs at lower dosages than the other organic acids. Weaned piglets are those who have been whose mother feed has been stopped, and fattening pigs who are being fat, which are having more fats in them. And so at the lower dosages, their growth performance enhances with the use of this formic acid or other acids, and rather the use of other acids and salts. Formic acid seems to enhance the growth performance of piglets, both weans and fattening piglets. In the poultry industry, formic acid has long been used to prevent the growth of pathogens in feed and feed materials. So along with this, for piglets or in the poultry industry also, formic acid has been used to prevent growth of pathogens in feed and feed materials both. Blends of formic acid with propionic acid, lactic acid, or medium chain fatty acids have broader antimicrobial effects than formic acid alone. If we use the formic acid alone, much better to use the formic acid with propionic acid, lactic acid, or medium chain fatty acids for increasing their antimicrobial effects. So they blend with other chain acids like those which I have mentioned here. Are better to use the blends of formic acid with these acids for their antimicrobial effects. Pharmaceuticals and food additives. Pharmaceuticals and food chemicals have been estimated to be the largest single sector of formic acid used in Asia, mainly in China. So formic acid is used as a synthetic intermediate for various pharmaceuticals and food chemicals, including synthetic insulin, purification of recombinant insulin, caffeine, aspartame, and vitamin B. All these chemicals, when are being used, the formic acid is used as a synthetic intermediate for that. It is also used widely for pH adjustment during the manufacturing of various chemicals. As we have seen before, it is used for regulating pH. So when we need to do the pH adjustments during the manufacture of various chemicals, we use formic acid. Other applications in food include salmonella decontamination and used as a preservative. A236 allowed in the USA but not in the European Union, EU, Australia and New Zealand, and as a flavoring agent. So the other uses of formic acid includes salmonella decontamination. This is that this is having antibacterial effects also. So salmonella decontamination is done by the formic acid use, and it is allowed in USA. E236 it is used as a preservative over there, and it is used also as a flavoring agent. The use of formic acid in food preservation includes fumigation of fruits such as apples, cherries to reduce post-harvest decay. So the spray of chemicals like formic acid, for example, is done in a way that their decay is reduced, that is slowed down with the help of that fumigation of formic acid as a helpful agent to reduce the decay. Formic acid is especially effective in destroy fungal spores on the surfaces and on containers in which the fruits are stored. If there are some fungal spores on the surfaces of the fruits or on the surfaces of the containers in which they are stored, it will just effectively destroy formic acid will effectively destroy that fungal spores, and this will also be a way to help them reduce their decay by any external agent. In some food preservation applications, formic acid is blended with lactic acid or propionic acid. As I have already discussed, we have seen on the previous slides that it's better to use it blending with other acids. The mixture is minimally corrosive, but due to its low pH, it helps in destroy harmful microorganisms and prevents their propagation, thus prolonging the shelf life of the product. So when we are preserving the food, so when we are preserving the product, so there will be destruction of the harmful microorganisms, and their production, the propagation will be destroyed, or they will not be able to grow over there. So that will be very helpful for the food industry to prolong the shelf life of the product. Other uses include rubber coagulation. So formic acid is preferred choice for coagulating latex, which is a suspension of microscopic natural rubber particles, polyisoprene in aqueous medium. Now the surface of the latex particles are charged, which creates repulsion between them, preventing coagulation. In the coagulation process, formic acid neutralizes these charges, eliminating the repulsion. Now how it is helping in the coagulation of the latex? The natural rubber particles, polyisoprene particles, which are in the aqueous medium, they are microscopic natural rubber particles. They make a suspension in the aqueous medium. Their surfaces are charged. As the surfaces of the latex particles are charged. As they are charged, so they create repulsion between the that repulsion actually prevents the coagulation. So in a coagulation process, how formic acid is being helpful there, it neutralizes these charges, and this eliminates the repulsion for the repulsion in between them, and the coagulation will be then easily done. The process results in a consistent, high-quality natural rubber product. So the use of stronger acids makes the pH drop too fast and inhomogeneously. If we use other stronger acids, what will be the drawback? The pH drop will be too fast, and that will not be homogeneous. As a result, the latex coagulates unevenly if the pH drop is too fast, too speedily, and that is even not homogeneous. So coagulation will be uneven, and it will of course pose a negative impact on the mechanical properties. So weak acid like acetic acid, they are less efficient than formic acid, so there will be higher consumption of weak acids like acetic acid. So for avoiding both the effects of very strong acids and very weak acids, formic acid the best choice in that case. That can be used, that can will maintain the pH drop in a steady way, and that will too much consumption will also not be used of the formic acid, because it is not that much weak as is acetic acid. Gas desulfurization. Formic acid is used as a desulfurizing catalyst in flue gas desulfurization for coal-fired power plant. The power plants which are based on the burning of the coal, so there is sulfur also present. So desulfurization is a necessary process over there. Sulfur whose content in coal can be as high as 5%, that is released as sulfur dioxide in the firing process. Now capturing that sulfur dioxide by passing the flue gas through an aqueous limestone slurry, resulting in gypsum. Gypsum is calcium sulfate. Now when there is a limestone slurry through which flue gas is passed, so that flue gas will capture sulfur dioxide, that will make the adduct with that sulfur, the limestone slurry, and that sulfur dioxide will make make an adduct over there. They will make up calcium sulfate. So sulfur will be removed from there in the from the medium. Adding formic acid to desulfurization cycle increases the efficiency of sulfur separation. If we add formic acid for where we are doing the desulfurization, the efficiency of the sulfur separation will be increased over there. Formic acid is used in the stimulation of high temperature wells in oil and gas fields where the conventional hydrochloric acid systems cannot be adequately inhibited. When hydrochloric acid systems are not adequately inhibited in the oil and in oil and gas fields, for the wells from where the oil and gas are being extracted. So but high temperature is to be stimulated or to be maintained. For that cases, formic acid is used. Well acidification is done by pumping the acid into the well for dissolving limestone or dolomite or calcite cement, which is present between the sediment grains of the reservoir rocks. In the wells where there are reservoir rocks and there are sediment grains also, there is limestone, dolomite and calcite. All these salts are present over there in the form of hard material. So they are just dissolved with the help of that acid which is pumped into the wells. Formic acid has the advantage of good inhibition against pipe corrosion at temperatures as high as 200 degrees centigrade. That is possibly caused by a protective layer of decomposition products. So at 200 degrees centigrade, the temperature is too high, there is possibility of corrosion. But what happens when the products over there are decomposed? Their decomposed products make up a protective layer. So formic acid is very good for the inhibition of the pipe corrosion at so much high temperature. Now mixed HCl and formic acid can offer furthermore advantages. The mixed proportions give further advantages. So formic acid does not dissociate in the presence of HCl. So there is no reaction with the carbonates until the HCl is virtually spent. So formic acid, if there is HCl present, formic acid will not dissociate. So formic acid will be having no reaction actually with the carbonates if HCl is not spent or fully finished. So if they are mixed together, they are having an advantage that formic acid will not be dissociated, and so the carbonate, it will not directly react with carbonates, and that will the carbonate and will be finished. So the presence of HCl is helpful in for the formic acid. Its dissociation will be prevented. An HCl and formic acid mixture thus achieve greater penetration. So both of them, when formic acid will not be dissolved also, decomposed also, and so their mixture HCl and formic acid will then give a greater penetration into the well, and that will help to dissolve the salts which I have mentioned over there, so that the transport of the our like oil and gas will not be tough at that time, if the sediments will not be having these hard materials in the way. Formic acid as a source of hydrogen and carbon monoxide. Under hydrolysis conditions, the formate ion can form a bicarbonate ion and hydrogen ion. You can see here the formate ion, when it is hydrolyzed, it can make up a bicarbonate ion and also along with that a hydrogen ion. So the formic acid, when is in the form of like if proton is removed or formate is formed, this formate is whenever hydrolyzed, it will be giving hydrogen gas. Both palladium and charcoal have been found to be active as a catalyst. Dehydrogenation reaction. So formic acid, for example, dehydrogenation reaction is promoted by metal catalyst. So palladium and charcoal both can be used for dehydrogenation, and this reaction is promoted by metal catalyst. So the reaction you can see below, formic acid is giving carbon dioxide and water, and heat of reaction is heat is being evolved in this reaction, and that is 31 kilojoule per moles. So formic acid is just being dehydrogenated and being converted into carbon dioxide and water. So you are seeing that formic acid in the form of formate is when hydrolyzed, it is giving carbonate and hydrogen gas, and formic acid itself when is dehydrogenated in the presence of metal catalyst, mostly when they are promoting the dehydrogenation, or in the presence of palladium is also a metal catalyst, or in the presence of charcoal, they all are being active catalysts for the dehydrogenation of the formic acid. There has been growing interest towards the formic acid or potassium formate based hydrogen generation in fuel cells. So the generation of hydrogen in the fuel cells, these two are being increased. Their interest is there is a growing interest for the formic acid and potassium formate based hydrogen generation in fuel cells. Now, long operation times and instant recharge with no dependence on electrical socket are the advantages when applied in portable devices. In portable devices, the advantages which are of the fuel cells which are hydrogen based fuels cells containing formic acid or potassium formate based hydrogen generation fuel cells, they are having a long operation times and instant recharge, and there is no dependence on the electrical sockets, because as far as fuel is over there for the fuel cells, they will be operating. You need not to recharge them from the electrical sockets. So, and they will be having a long time for operation. They will be able to be used for longer times. Their recharge time is the need for the recharge is after a long time. So decomposition of formic acid in the presence of strong acids like sulfuric acid is a clean source of carbon monoxide for carbon monoxide based chemistry. Now, if we need carbon monoxide, what can we do? We can decompose formic acid in the presence of strong acids like sulfuric acid. So we can decompose formic acid and we can produce carbon monoxide from there. That will be helpful where their carbon monoxide is further used in chemistry. So this is also a source for the carbon monoxide, the formic acid, as well as it is a source of hydrogen. Formic acid or its salts can be used as a hydrogen source in chemical reactions without formation of hydrogen as an intermediate Leuckart reaction mechanism. So if we want that, we don't want to use hydrogen as an intermediate directly, formic acid or salts can be used as a source of hydrogen for the chemical reactions. Like example is Leuckart reaction mechanism. The reaction known as transfer hydrogenation is selective, and that is catalyzed by many metals, even zinc powder. So there is a reaction that is called hydrogen transfer hydrogenation, that is catalyzed by many catalysts like zinc or many other metals can be catalyzing this reaction. That is a selective reaction. Transfer hydrogenation as a selective reaction. When chiral catalyst complexes are used, formic acid can serve as hydrogen source in asymmetric hydrogenation. Now when we are doing the when we are using chiral catalyst complexes, the complexes which are containing chiral moieties and they are catalyzing the reactions, so we can use those chiral catalyst complexes. So we can use for asymmetric hydrogenation formic acid as a source for hydrogen in that. So this is a common reaction step in the synthesis of many fine chemicals and pharmaceuticals, where the hydrogen source is formic acid for asymmetric hydrogenation. The source of hydrogen is formic acid, and where there are chiral catalyst complexes are being used. So when we are doing hydrogenation, we use catalysts also, and if there are chiral catalyst complexes, for them most commonly formic acid is the source of hydrogenation over there. Cleaning agents. Formic acid has some use as an active ingredient in commercial cleaning products, such as descalers, which remove scaling over some things, like remove the crust being formed of different salts, rust removers, multipurpose cleaners, degreasers, and institutional laundry products. So formic acid is an active ingredient of all these cleaning products. In descaling, calcium salt forms when calcium carbonate is dissolved by an acid. It's descaling, like its removal is taken place. The more readily soluble this salt is, the lower is the risk of salt deposit that reduce acid effectiveness. Where there is some acid is being used that will react with the calcium carbonate, and so calcium carbonate will be dissolved furthermore in the acid. So descaling must be done of these salts. They are risk of the salt deposit, and then they will reduce the acid effectiveness whenever the acid will be used. In bathroom cleaners, it is claimed to combine the properties of an efficient descaling agent with those of a biodegradable bioacid. So a biodegradable bioacid is used, and some descaling agent is mixed for the bathroom cleansing. Solvent use. Formic acid can be used to dissolve polyamides, for example nylon 66 and nylon 46, or silk, to prepare fibers and membranes. So when we are going to prepare fibers and membranes, we have to dissolve polyamides or silk. We use formic acid. It is also useful component in semiconductor cleaning solutions. So where there is a cleaning semiconductor cleaning solutions are being used, it is a useful component in the semiconductor cleaning solutions. The cleaning solution with which the semiconductors are being cleaned, formic acid is used in those cleaning solutions.